Okay, yeah, so I'm going to talk about approximation guarantees for data-driven algorithm design. This is based in part on a paper with Vadehi Srinivas, and in part based on thoughts from a course that I co-taught with Ravi Sharma last year. So what I'm going to do is I'll take 5 minutes just to say a little more about data-driven algorithm design, reinforcing some of the themes from Nina's talk, and then go on to all right. Then I can't gesticulate. Okay, no, but good idea. All right, great, thanks. And then I'll go into particular approximation guarantees for data-driven algorithm design. So, okay, so data-driven algorithm design in general. So, right, if you want an algorithm to do particularly well on problem instances coming from some domain, why not train it or tune it on typical instances coming from that domain? And, so for example, some motivating cases we'll get back to, solving, say, matching problems coming from a particular resource allocation domain. You could think of something like clustering news articles by topic. You could think of route planning problems, logistics problems, planning and scheduling problems. In all of these cases, it makes sense to use past data to do, find an algorithm that will work better on the problems instances you care about. And in fact, this is what companies implementing algorithms actually do. And so, is there something we can say about this theoretically? And as Nina described, the answer is indeed yes. And it's a recent direction with a lot of exciting work, really interesting mathematical and algorithmic techniques. And the high-level idea, as Nina mentioned, is we can define a parameterized family of algorithms typically motivated by one or more algorithms that has either, say, good worst-case performance or good empirical performance in practice. And that'll give you a nice family. And then given a sample of typical problem instances, say IID draws from some distribution, maybe I'll put this back, actually. All right. Wait, let's see. Okay, then, I guess not. Okay, and then try from that to learn a good setting of the parameters that you expect will do well on future instances. All right, and so there are sort of challenging and interesting statistical and generalization questions, especially when the algorithm behavior can be a highly discontinuous function of the parameters. It brings in a lot of interesting mathematical techniques, as Nina pointed out. Also challenging algorithmic questions here. And you can also aim for online regret guarantees, again, with challenging analytical and algorithmic questions there. And actually, to learn more, I taught a course on this with Ravi Sharma. The best way to learn, of course, is to teach. And also, Nina Balcan has an excellent book chapter on this topic. And here just gave a non-exhaustive list of some particularly nice papers that I think are really inspiring. Okay, and just to give actually one example, it's not one that I'll talk about later, but just to kind of clarify the algorithmic challenge. So let's think about biological sequence alignment, say DNA, protein sequences. And this comes from a paper of Nina and others from JCM 2024. So think about this problem. So typically the way you'll do it is the sequences are aligned using dynamic programming, but using different costs for mismatches, for where you're inserting indels. You have these blank spaces for how many gaps. So there'll be costs associated with those. But what should those costs be? So the data-driven algorithm design problem. Okay, so given an instance, it's a dynamic programming problem. But the data-driven algorithm design problem is given a collection of pairs where maybe you know the ground truth, biological, appropriate way that they align. Find costs such that if you then use dynamic programming, you would produce these or close to these matches on those and then generalize to new pairs. So the algorithmic problem here is the problem of finding the cost functions so that you could then use it in dynamic programming. Okay, so then there's the statistical generalization question. How much training data do you need to guarantee that good performance in the training data will translate good performance on new pairs? And then the algorithmic question of how do you actually efficiently find the best setting of costs? Okay, in this case, good good corresponds to solution quality, I'll be focusing on the case where good performance corresponds to running time. But it's really to what, what you care about. Okay, so now let me get to the topic of approximation algorithms for data-driven algorithm design. And the idea is, let's try to use ideas from approximation algorithms and competitive analysis in the online case to try to simplify the algorithmic challenge a bit, maybe even make it easier to compare to some stronger benchmarks, but we'll willingly give up some, constant factors or logarithmic factors or polynomial factors, as we need. I'm going to focus on something called warm start initialization. I'll get to what that is. Something's called meta-learning, where you're trying to figure out the starting point of your algorithm. It's just a particularly well-behaved, it's probably the simplest of all these settings to deal with. And so that's what we'll be looking at. We'll see a cameo appearance of the k-server problem here. And just to point out, we'll be losing multiplicative factors with respect to our benchmark. So the perspective is that, we're hoping the thing we're competing with is substantially better than a kind of generic algorithm, a generic start for the algorithm. Okay, so warm start initialization. So many algorithms run faster if you initialize them with a solution that's close to the right answer. And so some classic examples, for instance, Ford-Fulkerson max flow algorithm. Typically, you start from an empty flow, but if you start from a different flow, if that flow is close to the flow you're going for, close in L1 distance of the flow vector, then actually your algorithm will run much more quickly. The Hungarian algorithm for min-weight perfect matching, and you can think of gradient descent. In general, if you start closer to where you're hoping to end up, your algorithm will take fewer steps. Okay, and we can kind of think of this, and I'd like to think of this as having a metric space on solutions, where d S1, S2, the distance from S1 to S2, represents the cost if you start from S1 as your initial starting point, and you're trying to solve a problem instance where its actual solution is S2. All right, you're hoping its solution is S1, it's actually S2, but if they're close, your algorithm will run more quickly. You can think of this as an upper bound. Maybe be able to prove that your running time of your algorithm has an upper bound, depends on this distance. And the distance could be something abstract or it could be something concrete, like in the case of max flow, the theorems shown are that the L1 distance between the flow vectors can be used as an upper bound. Now, in reality, it takes time to check a solution even if it's handed to you. So really, the distance of a point to itself should be bigger than 0. That's fine. That doesn't affect anything. We will assume it's symmetric, that this thing is symmetric, so that the cost, if the right answer is S2 and you start from S1, that'll cost the same as the other way around, that you start from S2 and the right answer is actually S1. Okay, we'll need that. And so what's nice with this kind of way of thinking is conceptually now, running an algorithm from a starting point is like growing a ball around it. You don't know where the solution is you're looking for, but you can think of it as growing a ball kind of at unit rate, starting from your solution, and then eventually you'll hit that point, that you're shooting for, right? So that'll be, by the time you get to, here, I'll just draw a little dot here, like at this point, oh, it didn't actually draw, okay, never mind. Okay, so you're just growing this ball until you actually hit that solution. So you can think of it that way. It's a nice conceptual way to think about what's going on. Okay, so what's known? So in terms of theoretical guarantees, there's been some recent work on learning good initialization for a distribution of problem instances. So there's work on doing this in the context of matchings and work on doing this in the context of network flow. And then also in the online case, competing with the best single initialization for an adversarial sequence. So now in the second case, we're not assuming our instances are drawn from some distribution, it's just some sequence. We have to solve problem instance 1, then instance 2, then instance 3. Who knows where they're coming from, but we'd like to perform nearly as well as the best single initialization that could be used for all of them. And this nice paper here analyzed that problem that Nina talked about, this learning predictions for algorithms with predictions. Okay. the starting point here is, what if the best single initialization maybe is not good enough? We'd like to maybe do even better. Maybe if we're willing to lose some multiplicative factors, we could even compete with stronger benchmarks. And I'll just briefly talk about two results in this direction. One, what we might want to do is learn a mapping from features of the instance. Maybe we're trying to find a matching in a graph, and with some simple features. How dense is it? Something about, you know, the structure of the degrees, whatever. And use that to an initialization. So maybe we'll run some function h. It'll give us a number out 1 through k to tell us what type of instance it is, and then we'll use that to figure, okay, then we'll use, say, think these red dots will be, say, the initialization. Which red dot will we use? Okay, so which initialization? So let's try to learn a function and initializations associated. And the second, we'll look at online algorithms. We're trying to compete with the best adaptive sequence of worm starts, or even the best adaptive sequence of k-worm starts. So here we'll lose some polynomial factors. Okay, so let's start with the first one. Okay, so let's assume we have a distribution over problem instances. Well, so one thing we can do is we can draw a sample of them. Great. We can find their solutions. Those are blue dots. The blue dots are the solutions to the sample of instances that we've drawn, our training set. We could solve the k-median problem, or approximately solve it, to find the k best initializations. Those are the red dots. Okay, so if the cost of solving an instance from a start is that distance, then the k-median problem gives us what is the best set of k initializations if for each instance we could magically find which red dot would be the best one for it, okay? But let's do that. Let's solve that k-median problem. And then now, okay, so just to be clear, we have instance space and solution space, so that the thing on the right is the solution space. Now, one challenge is the best set of initializations to use depends on the mapping that we find. So if we're able to find a mapping that looks like this, then indeed the red dots are the best initializations to use. But if the best mapping we can find looks like this, then these red dots aren't the best thing to do. Now, of course, the first mapping was better. Okay, here we have a mapping that maps all these guys on top to 1, those to 2, and those to 3. It's not as good a mapping. You know, we really prefer the first one, but we might not be able to find the first one in our family, because after all, this function that's mapping instance to type, so we're going to say, hey, is this a type 1 instance, a type 2 instance, or a type 3 instance? It has to be a fast function. It can't be that the way it works is it first solves the problem to figure out which initialization to use. That would be stupid, right? So it's got to be something that's fast, and so it may not, you know exactly where that solution is going to lie. So we don't really expect there's going to be a perfect function. Right. So here's the question. If we had that mapping, then we should have used these as our starting points. But now we have a really funny optimization problem. We want to solve simultaneously for a mapping and a set of initializations to use. And that's kind of confusing. What we'd really prefer to do is, can we first just solve or approximately solve the k-median problem, a well-defined, algorithmic problem, and then once we've done that, now go ahead and try to find the best mapping H. And the nice thing is now the learning problem of trying to find the best mapping H, this is just a standard k-way ERM with a cost function problem. So what do I mean? What I mean is, let's say that we solved the k-median problem, and the k-medians are 1, 2, and 3 like that. Now, for our learning problem, trying to affect the best H, we can just think of this as there's a cost matrix where for that blue dot, assigning it label 1 has the length of that green line is the cost. Assigning it label 2, the length of that green line is the cost. Assigning it label 3, the length of that green line is the cost. So there's now a well-defined cost for which thing you assign. Now we just want to solve for the H that on our training set, minimizes cost according to this cost matrix that we have. So that's a standard learning problem. So we'd like to do that. And so, okay, so the question is, can we do that? And so claim, if we optimistically solve the k-median problem first, assuming that, any H is possible, we get some centers, C1 through CK, and then find the mapping that has lowest loss with respect to these centers. So it minimizes the sum over all instances in our training set. So capital IJ is the jth instance in our training set. And then the distance between the center that H is telling us. So H says, hey, this instance is type 1. Okay, so that's C1 to that its actual solution, SJ. So that's the cost. We want to minimize that sum. That's our training loss. Then that will be within a factor of 3 of the best pair, H star, C star. So if we're only going to lose a factor of 3, we can take this hard optimization problem and break it into 2 simpler optimization problems. K-median, which there's lots of algorithms for. You can get a constant factor approximation, and then an ERM with a standard kind of loss function problem. Okay, so this is an example of a kind of a statement we can get. Yeah. So for example, maybe this is the best H we can find for those. And so all on the one side they all go to that red dot 1. On this 2 side they all go to red dot 2, and on the 3 side they go to red dot 3. Maybe that's the best we can find. And then once we can do this for our training set, we can now use the technology of the form that Nina talked about to get generalization bounds. Look at how large a sample size we need to do well in future instances using these dual function classes and so forth. We can just, so that's already been done. So that's great. Okay, to argue this, we'll need a technical assumption, which is that, I'm just going to briefly talk about this, so that if a particular mapping is in our family, then so is any relabeling of that. So if you can call that 1, that 2, that 3, you can call that 1, that 2, and that 3. In fact, you can call that 1, and that 2, that those are all in your family. Okay, so we'll need that. And then the theorem comes basically by applying several triangle inequalities. I'll just take 1 minute to kind of roughly say how it goes. Okay, so here's the analysis idea. So the thing that we find the H that works best for the centers C1 through CK found by the K-median problem. Great. That's at least as good as the cost, as the best phi of H star for these centers, because after all, we found the H that was best. So it's at least as good as this other thing, phi of H star for these centers. What we really care about is H star of its own centers, C star. All right. Okay, well, that's at most, okay, so phi of H star for these centers, you can think of as first going from these centers to its own center, and then from its own center to the actual solution to the problem instance it's trying to solve. So that's a triangle inequality there. So in particular, let's say that's the jth solution. That's the associated center of phi of H star. So that's its associated center, and that's the center that it would have used. So it's so the thing that we have to pay for distance from SJ to that center is at most the two green lines. Okay, the lower green line, that's what H star is paying anyway. Okay, that's one of the 3. We just need to pay for the upper green line. Okay, so how do we pay for that? So I haven't said what phi is. We can define phi to be for each green dot, for each C star, what's the closest red dot? What's the closest K-median center? So that's how phi is defined. So we care about that green line up there, okay? And so that from that green dot to that higher up red dot, since that's the closest one, that's less than or equal to the distance of the center to the thing that SJ would get matched to in the K-median unconstrained optimal. Okay, that's great. And then that's at most, this plus this, and this is just another one of what H star pays, and then this is the unconstrained optimal, which is a lower bound than what H star pays. And so that gives us our 3. Okay, so there we go. The unconstrained optimal plus 2 of the H star, C star cost, which is at most 3. Okay, so just to show how kind of if we're willing to lose some constant factors, we can take this kind of hard optimization problem and break it into some easier problems. Okay, so that's the summary. Okay, so now let me switch to talking about online adaptive initialization. Okay. So what if our problem instances are not IID? Can we compete with the best adaptive initialization or the best adaptive set of K initialization? So for example, if maybe we first see a bunch of instances whose solutions are way over there, and then we see some instances whose solutions are more over here, then there may be no single initialization that's great for all of them, but maybe we could use the left red dot for the first problems and then move it over to the right and use that red dot for the later problems. All right, if we had known in advance this is what the world would look like, we could have done that. All right. Of course, we don't know in advance the world's going to look like that, so can we compete with the best adaptive initializations? All right, now, for this to make sense, we have to charge the thing we're competing with for movement. All right, otherwise, the optimal thing in hindsight was to magically have guessed the solution to the instance we're about to solve and pay zero cost. Okay, you can't do that. So you got to move it. You have to pay to move it. So if the thing we're competing with decides to change its initialization from here to there, it's got to pay for that distance. Okay, so that's the thing we want to compare to. Okay, so that kind of makes sense as a comparator. So for example, for k equals 1, we're comparing to the best, what's the best center or starting point C1 for the first problem, and then we're allowed to move it from C1 to a new starting point C2, use that for the second problem, then move it again from C2 to C3, use that for the third problem, and so forth. That's the thing we're comparing with. Okay, so we want to do nearly as well as that. And I'm here and I'm going to consider the case where there's no feature information, but I think it'd be an interesting problem to try to extend this kind of analysis to the case where there's feature information. So there's no mapping agent here. Okay, so just to give some examples here, for example, this scenario is pretty good for the case k equals 1, a single moving initialization. On the other hand, this case would be bad. So this is the same as the one above, except they go back and forth. First, second, third, fourth, fifth, sixth, seventh, eighth. Here, there's no instead of moving one around, you'd like to move two around. Here you could have two different ones, and you could kind of compare to for each one, having getting to choose the best of those cases. So if you had two initializations in mind, and then for each instance, which of them would be best? So we'll have two moving around instances, and we want to compare to the algorithm that in hindsight, magically knew which of those two to use. Okay. So first claim, there is a very simple factor of 2 approximation for this for the case k equals 1. And what is that? The algorithm is just use the solution Sj to the problem you solved yesterday as the warm start for the problem instance ij plus 1 that you're solving today. Okay, so just use yesterday's solution as the warm start for today's problem and so forth. If you do that, then you're paying the cost of this green path. And just to make this precise, let's say that S1 is the generic start that you start with at the very beginning of the whole process, and I2 is the first instance. So you pay that. Just all these green lines is what you pay. And analysis, well, we want to compare to the best sequence of starts. So maybe the best sequence uses that left red dot for a while and then moves it to the right red dot. So our cost is the distance between all the solutions directly. And that's at most the cost, because from S1 to S2, we could first go to the C1, and then from C1, move it to C2, then to S2, and then from S2 to C2, then to C3, and then to S3, and so forth. So what we're saying here is that this green path is at most the cost of move to the red dot, then to the next one, then back to the red dot, then to the next one, to the red dot, and so forth. This is kind of like, the MST, TSP, right? So we're just taking the optimal and doing each step at most twice. So this is at most 2 times the cost of the optimal sequence. So a nice factor of 2 is just use the previous instance's solution as the warm start for today's instance. Now what about trying to approximate the best set of k adaptive initializations? Okay, so now this is going to be a little harder. Well, here's one idea. If we knew where the k initializations were, Okay, so if we knew that each new problem instance was likely to have a solution near one of k possible warm starts, C1 through CK, we just didn't know which one to use, then if we're willing to lose a factor of k, we could just run k copies of our algorithm in parallel, growing balls around each of them at a rate, 1 over k, factor. So we're just going to, spread our time among those. So instead of growing a ball around a single instance, we could just grow around all of them and just keep growing until we happen to solve the problem instance. And this will be only k times slower than using the best start. So if we're willing to lose a factor of k, then we can do within a factor of k of the best of these starts if we didn't know which of them to use in advance. Okay. Okay, so that's one idea. Of course, the problem is we don't know where these C1 through CK are that we're competing with, and they're changing over time. Okay, so that's a problem. All right, so here's a second idea. With only a constant factor loss, we can assume that the warm starts we're competing with are actually solutions of previously seen instances by using a triangle inequality similar to the analysis we did for k equals 1. So with only a constant factor loss, we can assume that the things, we don't know where the warm starts we're competing with are, but we can assume they are solutions to previously seen instances. Okay, so that's something like this. The thing we're comparing to, these are the first two, say the solutions to the first two instances, and the third one comes along and we use this one, fourth one comes along, we use that one, the fifth one comes along, we use that one, the sixth one, we use that one, seventh one, we use that one, and so on, for instance. Of course, one thing is we don't know which are the currently active ones. If we knew which were the currently active ones, then we'd be great. We could just use those, but we don't. All right. And notice this is a lot like the classic K-server problem where you're trying to maintain K-servers and you get a new request, but it has two key differences. One is that here it's harder because we don't know where the thing is we're looking for. Normally you know where you're going and you can decide then which one to move. Here we don't, so we have to grow these balls until we kind of hit the solution. Okay, and that's why we lose this extra factor of K. So we don't know the location of the new point we're trying to serve. We just can grow these spheres. On the other hand, it's easier because there's nothing saying that our algorithm has to maintain k starts. It could maintain more starts. It could do anything it wants. We just care about the total time. We're not limiting ourselves to some particular form of the algorithm. And also a little different because actually ideally we'd like to get a simultaneous guarantee for all k. What I really want is a guarantee here that says that our cost, because we don't know, the sequences we're going to see. Is it easy? Is it hard? We'd like to do nearly as well as the best out of all values of k of some function of k times the cost of the best set of k adaptive initializations. So, if it's the kind where they kind of just move around a little bit like this and k equals 1 is good, then we want to use k equals 1. If they kind of bounce, then maybe k equals 2 or k equals 3. We want to do nearly as well as the best of these with an algorithm that doesn't have k in advance. Yep. Okay, idea 3. How about let's start from all previously seen instances and just run in parallel from all of them. I mean, that'll include whichever one, the optimal is using. Now, of course, the problem from here is there's too many. It's not fixed with k. It's the number of instances is growing, right? So this will lose a factor. It's not good. Our performance is going to degrade. Our approximation ratio, or competitive ratio, will increase with the number of instances we've seen. So that's not good. Okay. Idea 4. Well, what if we favor more recent solutions? On instance t, let's spend 1 over f of I fraction of time using the solution that was I time steps ago for some function f of I, where 1 over f of I sums to 1. Like maybe, like 1 over I squared, something like that. 1 over I log I squared. So something that sums to constant. So we're going to put more time on the recent ones and less time on the ones longer ago. And this makes sense because if you look at the optimal trajectory, it doesn't always have to come from a recent instance, but most of the time it should come from a recent instance. Because if you use an old instance to solve a new one, then you've moved an old one to a new one and now it's become new, right? So it gets updated to the current solution. So most of the time you're using pretty recent ones. Unfortunately, this doesn't actually work. Not quite enough. It's not quite enough to get a polynomial in K-bound. Okay, idea number 5. Let's do the same thing, but here's one thing. These balls are growing at different rates. The more recent ones are growing faster. The older ones are growing slower. When a recent one, when a fast-growing ball eats up a slow-growing ball, you can kill that slow-growing ball. It's not doing anything for you anymore. The faster-growing ball contains it. The slow-growing ball is useless. Kill that one, renumber things, reallocate your time. That turns out to work. So that's enough to then give you this polynomial in K approximation or competitive ratio. And the final result you get here, well, either K to the 4th or K cubed approximation, depending on the exact model for counting costs. So it's a question of, do we count, how expensive is it to tell the distance between 2 points? Do we count that? Do we have to solve something to figure that out, or is it kind of given for free? So that's, we get different bounds. We know a different algorithm that gives us K squared if you're given the K in advance. So someone says, I care about this particular value of K, then we know how to get K squared for that using a different algorithm. And the best lower bound we know is omega K. So that K that comes, even if you knew where the instances were, you just didn't know which one to use, you're getting a K from that. So the nice open question is, where is the right answer here? Maybe there's some technique to get a better lower bound. Maybe K squared is right. I don't know. Can you get the K squared without having simultaneously kind of for all K? That I don't know. Yeah, and to go below this, you would then need to use feature information. Okay, so let me just wrap up here. So more broadly, this is just one kind of data-driven algorithm design where we're using past instances. So in general, in data-driven algorithm design, we want to use past instances to find good algorithm parameters. In this case, the case of warm starts, the parameter of the algorithm is the starting point. So Nina talked about cases where there's lots of different parameters. There's in the knapsack case, there's these functions. In the case of rounding SDPs, other kind of things. In the case of clustering, it might be you care about the properties of the distance function and so forth. So here, the algorithm family is the family of solutions of starting points. So the family of starting points. So you kind of fix the algorithm except for the starting point, and that gives you this family. We want to, we're looking at that family. Okay, so it's just, as I mentioned, it's particularly nicely behaved family for this sort of analysis. More generally, right, data-driven algorithm science considers families of algorithms defined by all sorts of things, and it'd be interesting to see if the perspective from approximation algorithms could help in giving more provably efficient ways to find near-optimal algorithms in the family. And I think it's reasonable to say, given access maybe to some oracles. So maybe given access to natural ERM oracles or various sort of things that, that are natural to assume. Or can we, either find a near-optimal algorithm or do nearly as well as the best algorithm in the family, or and so forth. Yeah, that's it. Chandra.
Is an philosophical question. So I guess if you think of it as improve the running time of an algorithm by a long function, how do we account for the cost of all this pre-processing and storing like big solutions? And so how do we know the benefit of the warm start improving the cost of a new instance versus the cost of mapping?
Oh, okay, good. So kind of the question about the model, right? So in the second part, for example, the algorithm will be maintaining, okay, so what does the algorithm look like? The algorithm is sort of, you know, multiplexing. It's going to say, okay, here I'm going to run this algorithm for a while, stop it, I'm going to, you know, run this one. So you know, you're remembering a bunch of different starts. You have to, so, you know, checkpoint your state and do a context switch. So in our setting, we haven't assumed any cost for a context switch and so forth. You know, we can sort of in parallel. The assumption here is that you can run two algorithms in parallel, you know, and then you just slow them down by a factor of 2. If there's a context switch, you know, yeah, one could sort of, it could be interesting. Maybe there is a way to think about this where there's a switching cost for switching from one to another, because you have to pull it out from you know, slow memory back into cache or whatever it is. So I think that, you know, probably one can build on kind of, you know, the stuff people that we all looked at in the 90s and those kind of problems, you know, for this sort of thing. For the first one, where there is a function, there it's just at the very beginning, you're going to just apply a quick function. So there it was how fast is h? So there that requires a little bit of, you know, some taste in what your function is allowed to do in mapping the instance to, well, which kind of instance is it? As I said, that if you solve the problem, to say that's kind of silly. So you want something that's a little bit fast. But you just do that once, and then it says, oh, this is instance type 7. Let me pull up, you know, start 7 to use. It's not too bad. It's not too bad. But you're right, you know, one has to do this, you know, especially this issue of this distance function. How easy is that to compute? Is it something simple like an L1 distance? Is it something that's more implicit? I think those are interesting questions, but yeah.
Yeah, so if you look at this one start comparing with the benchmark, am I audible by the way?
Yeah.
Yeah, good. Okay, so I can, yeah, don't worry. So, this looks suspiciously similar to like this online learning type of problem, right? Like regarding the minimization, like you can, or even view each work start as a band-aid to try to sample from it and then try to keep up with the best benchmark.
Yes. So it is very much like an online. In fact, the previous papers on this looked at this in terms of regret bounds. So regret bounds are really nice because there your ratio is going to 1. You just have an additive gap, which is, you know, sublinear. And so you know, regret bound is like a competitive ratio of asymptotically 1. And they're able to use that to do nearly as well as the best fixed start. But now what we're doing here is saying, well, we're going to do a trade-off. We are going to lose constant factors, so the regret is going to be horrible, because the additive regret, because the multiplicative factor, but we're going to compete with something stronger, which is either a start that's allowed to move around or even k things that can move around. So it's kind of a trade-off. So, you know, do you want a really tight thing with respect to a single fixed thing or a looser thing with respect to something that can move around? You know, you could even imagine, you know, and combining that. But yeah, so that's the trade-off. This perspective says, hey, let's give up some constant factors, some other factors, see what we can compete with.